Hi everyone. This is a supplemental lecture or supplement to lecture 23 on turbulent pipe flow. And today I'm going to review with you how to calculate the friction factor for turbulent pipe flow. This is kind of exciting. Hopefully this will be meaningful to you. I'll just really quickly review the geometry here. We've seen this before. We have a cylindrical pipe. It's in cylindrical coordinates, so I have z down the axis, r radially, and then the theta, which I guess I haven't drawn up here, but I can, is the direction around. And I have z equals 0 out here at the front of the pipe, z equals L at the end of the pipe. My velocity is going to be unidirectional down the pipe, and I have an initial pressure and then a final pressure. And the new thing with turbulent flow was we said we needed averaged equations. So we did this Reynolds averaging. So now we have an averaged continuity equation. And, pardon me, we also have an averaged Navier-Stokes equation. And so in the Navier-Stokes equation, we have the average velocity, the average pressure, and remember this is a time average, and then I have the divergence of our averaged viscous stress tensor, and then a new guy, tau star, which is what I called the Reynolds stress tensor. Okay, and I guess I should put a couple lines near these guys here to make sure we remember their tensors. Okay, so if I plug all this in for unidirectional flow, this simplifies to dp dz plus this guy, and notice that this looks pretty familiar to what I had before, if you remember the day we talked about non-Newtonian flow. This looks, I think, almost identical, except now I have this other guy out here. All right, and the process to solving this is a little bit different, and I'm not going to require for my class that you know this, but the notes are posted online, so I'm going to skip the math. But what this gives you is a slightly different velocity profile. You get something where you have a log, a natural log in it, and it's in terms of the, it's often written in terms of the wall shear stress. All right, and so what we want to do is be able to calculate the friction factor given this velocity profile. All right, so how do we do that? Well, there's two steps to doing this. The first step is we need to calculate the average velocity u. So that's the average velocity. And then in the second step, you remember, we want to get tau w. And then I said that the third step, actually, so there's three steps, but in this case, the tau w is going to be actually pretty trivial. Then we rearrange to get f using our relationship that we know for f, which is f is tau w over 1/2 rho u squared. Okay, and these three steps are what I said earlier for getting the friction factor. But in this case, because tau w already exists in this guy, it's going to be a little different than the case that we did earlier with the laminar flow. Okay, so let's do these steps. So part A is to get u. So, well, what's u? We've seen this formula before. It's the average velocity. So I have the spatial average now. So I have 1 over the cross-sectional area times by the average velocity, or the velocity time average, because that's what I get out of my turbulent flow, r dr d theta. Okay, and what I want to do, so I can rewrite that double integral here, this area integral. I'm going to put it, let's see, I'm going to have whatever it was in between. And I'm going to switch. I'm going to have d theta and then r dr. And from theta, I'm going to go 0 to 2 pi, and then this will be 0 to r. So to do that guy, I can just pull a 2 pi out. 2 pi comes out, And then in the bottom, I have pi r squared. And now I'm going to have the integral from 0 to big R. And then I need to take this Vz up here and plug that in. So that Vz is tau w over rho to the 1/2 power. And then in this bracket, 2.5 natural log of the square root of rho tau w times big R minus little r divided by mu, close the bracket, plus 5.5, close the brace, I forgot the brace up here, times r dr. Let me just make sure that that's right in my little notes I have over here. Okay, and that's right. So this is going to make my life a little easier if I cancel. So I'm going to cancel this. I'm going to get a 2 over r squared. And then let me come up here and add a new page. Okay, and instead of doing this next line, I'm going to try and make my life a little bit easier by making some substitutions. And these substitutions have some physical meaning that we're just not going to talk about, but you're welcome to read about in your book, of course. So these are called wall variables, and I'm going to, they have a little plus sign on them. So the r wall variable is defined as the square root of rho tau w multiplied by r divided by the viscosity. And then I'm going to define this guy eta, which is going to equal r minus big R minus little r over big R, which is the same thing as 1 minus r over big R. And so I need to do a little bit of substitution. If I'm then going to substitute these variables in here and do my integral in terms of these. Okay, so to do that, I'm going to, let's see, rho tau w r over mu. Let me do that in a couple steps. So I have 2 over r squared, the integral from 0 to r of tau w to the 1/2 divided by rho to the 1/2. Quantity 2.5 natural log. And now inside the natural log, I'm going to have an r plus, which comes from that guy. Okay. And then I'm going to have, let's see, I pulled an r out. So then that will be a 1 minus r over r out there. Great. So that one now will become eta. And then plus 5.5, close that, r dr. Okay, so I made my inside of my natural log a little easier, but I still need to worry about these guys right here. So I can take, for this integral substitution, I can say, what is d eta? Well, d eta is going to be minus 1 over big R dr. So I can solve for dr, and so dr is going to be minus r d eta. Okay, that's not so bad. And then for r, I need to rearrange this guy. So that will make, let's see, r is going to be big R eta plus, let's see, no, not that. I'm trying to do the algebra in my head. If I multiply both sides by big R, that becomes a big R. Then I need to swap them. So I get big R minus big R times eta. Is that right? Double check. Yep, which is the same thing as big R times 1 minus eta. Okay, so now let me plug all those guys in. I can factor that out to 2 over r squared, integral from 0 to big R. Oh, I need to be careful about these bounds too. So these bounds, if these are in terms of r, so if I want them in terms of eta, if I plug in big R goes in there, I get 1 minus big R over big R. That's 1 minus 1 gives me 0. And then 0 plugged in here gives me 1. So, okay, so now those bounds are in terms of eta. I get tau w to the 1/2 divided by rho to the 1/2. And then 2.5 log of r plus eta plus 5.5 multiplied by, and then now I say this is r times 1 minus eta minus r d eta. Okay, great. So now look at this. So this r squared is going to cancel with that and that. And then that minus sign I'm going to use to flip that guy upside down. So now I want 2 tau w to the 1/2 divided by rho to the 1/2. Integral from 0 to 1. Give myself a little more space here. And now I'm going to have, let me just put a simple bracket, that's a little easier. 2.5 natural log of r plus eta plus 5.5, close square bracket, 1 minus eta d eta. Okay, so now I need to do these integrals. Okay, so I'm going to multiply these pieces out and do these integrals. Oops, I forgot, accidentally deleted that guy. All right, and I'm not going to bore you with the details, but the integrals that I'm going to need are 1 minus eta from, because that's going to, I have a 5.5 times that guy, so that's going to give me from 0 to 1. So if I use that one, it's going to give me a 1/2. And you can plug these in on your own some other time or do the full algebra by yourself. And I'm also going to need one that has a natural log of eta times 1 minus eta in it. And that's going to come from that product with that guy from 0 to 1. And that gives me a minus 3/4. Okay, so plugging that all together, putting those pieces back in, I end up with this 2 tau to the 1/2 divided by rho to the 1/2. And then I have 1/2 multiplied by 2.5 log r plus 5.5. So this was from that integral, and I am factoring out the 2.5 log of eta, which I can do right over here. So now this one is going to give me minus 3/4 times 2.5. Okay, because in this 2.5 log eta, that gives me 2.5 times minus 3/4. All right, so now I'm getting close to being done. I have, I just have to move some things around. So if I multiply through by 2, that 2 will cancel here, and I'll cancel a factor down there. So I can multiply that, 2, and then that becomes a 2 in the denominator. And this now becomes tau w to the 1/2 divided by rho to the 1/2 multiplied by 2.5 natural log of r plus, and then I have 5.5 minus 3/2 times 2.5, and that ends up giving me 1.75. Okay, so that is u. I'll erase this because I started kind of writing it a little lower. That is my average velocity. Okay, so that's part A. Part B, I said, isn't really a step because look, we already have tau w in the expression. Okay, so if you remember in the laminar flow, u was relatively easy. We didn't have these nasty log integrals to do, but then we had to find tau w by taking derivatives. In the turbulent case, u is a little bit harder because of this integral, but we don't have to take any of these derivatives because it's already in terms of tau w. So our life is a lot easier in that sense. So that makes step 3, though, a little bit different. So now we put them all together. Remember, and we want to use this guy. F is tau W, well, we'll put the 1/2 on the top. 2 tau W divided by rho U squared. That's the definition of the friction factor. So notice that if I just flip this upside down, I get 1 over F is equal to rho U squared divided by 2 tau W. And I can take the square root of both sides. Taking the square root of both sides gives me 1 over root F is equal to the square root of rho multiplied by U. And then in the bottom I have the square root of 2 and the square root of tau W. Well, look at that. This right here looks like something I already have, right? I have a U right there. Let me plug in the U that I've got into that piece right there. Okay? So let me do that. 1 over the square root of F is equal to, and I'm going to put over here a square root of rho over tau W multiplied by 1 over root 2 multiplied by U, which is the square root of tau W over rho, and then this square bracket, 2.5 log R plus 1.75. Okay, this piece and that piece cancel. And now I get 1 over root F. Scrolling down. Oh, I need a new page. Okay. I get 1 over root F is equal to 1 over the square root of 2 multiplied by 2.5 log R plus 1.75. Okay, so now wait a minute. I have this R plus going on. Let me play around with that a little bit. So remember what R plus is. R plus we just defined up here. It's this dimensionless number that we defined right there. It has square root of rho tau W R over mu. So let's rewrite that. Square root of rho tau W and then an R divided by mu. Well, we said that we had this tau W in here, and let's substitute tau W is equal to or use our expression for the friction factor. Let's solve for tau W for the friction factor. So right here, I can rearrange this guy and solve for tau W. So I'm going to say that's equal to F rho U squared divided by 2. Right? So now let me plug that in. I have the square root of rho multiplied by F rho U squared over 2. I'm going to put that whole thing under the square root. And then outside of the square root, I have R divided by mu. So R plus then becomes, well, I have a rho squared and a U squared, so that comes out. So I have rho U R over mu. And then inside the square root, I have F over 2. Okay, well look at that. That right there, that guy right there, is the Reynolds number if I swap D for R, right? So R equals D over 2. So I need a D over 2. So this gives me the Reynolds number over 2 times the square root of F over 2 inside the square root. Or this gives me the Reynolds number times the square root of F divided by 2 root 2. Okay, now let me come back out here. So I have 1 over square root of F equals 1 over the square root of 2 multiplied by 2.5 natural log the Reynolds number square root of F divided by 2 root 2 plus 1.75. Okay, now I can just rearrange a little bit and I'm pretty much done. I have 1 over the square root of f, and then I'm going to aggregate some of these things. So I have 2.5 over square root of 2 log of RE square root of f over, I'm not going to do it over anything actually. I'll do that, plus, then I have 1 over the square root of 2 log of 2 root 2, and this should actually, instead of be a plus, it should be a minus sign because it was in the denominator, plus 1.75 divided by root 2. Okay, so if I do all of that, I have 1 over root f, and I can plug these numbers in, and this gives me a 4.07 log 10. If I switch the logs, remember that let me write it over here, log base, let's see, 10 of x is going to equal natural log of x divided by log base 10, or natural log of 10, excuse me. Natural log of 10. All right, so log base 10, and this is RE square root of f. And let's see, this number gives me 0.601. Boom. There is an expression that looks very similar to the Prandtl-Karman equation that we used earlier in class. And this Prandtl-Karman equation, you remember, was on page 38. We can look it up. If I grab my book here real quick, and on page 38, we can look up what the Prandtl-Karman equation was. And the Prandtl-Karman equation is 38. That doesn't seem like the right one. 33. Oh, can't read an 8 in my book. Page 33. Let me fix that right here. Page 33 in the book. Well, that was even worse than before. 33. And this guy right there is a different number. That one just becomes 4.0. And this one back here is minus 0.4. So the empirical fitting, they take the same expression, but these numbers change a little bit. But that's basically the Prandtl-Karman equation that we just derived. Okay, I think that's all I have for you. Have a good one.